Welcome everyone to the last oral session of the day. I want to thank you all for coming. This is the final session of the day in what has already been a rather exciting day of exoplanet talks. So this session is the AGU AAS union session on frontiers in exoplanet science. This session is part of an initiative between the AGU and the AAS that is intended to help further broaden and deepen the connections between the communities of the two societies. So today's talks are meant to provide some information on where the different communities are and what sort of things they're looking at and what are the big picture questions in those areas. And this is actually the first session in a series of sessions that are being supported by the Kavli Foundation. And so we have the session here today. There will be another session at the AAS meeting next month, and we're also starting to plan for a workshop later in 2019. So a little bit about today's session. We're going to have a series of 5 invited talks. They will be, we're going to set the timer for 14 minutes, and things will start showing other colors at 2 minutes, so the speakers are aware of what's going to happen. We are also being streamed live, and there may be questions from online. And so we encourage people to use the app to ask questions that way. At the end of these 5 talks, there will be a discussion panel involving all of our speakers today. So if there are questions that we can't get to, we can circle back to them then. With that, we will start with the first talk, which is to be given by Sarah Ballard, and it is Planets in the Milky Way, Their Occurrence and Their Characteristics.
Thank you very much for allowing me to introduce this great session. And I thought in the time that I have to communicate 3 main ideas. I opened this talk with a piece of art that I first saw at an exhibit called The Art of Astrophysics at Boston University. The reason why I've opened recent talks with it is because it communicates a feeling of multitudes. So in addition to sort of these individual motes of dust floating in and out of focus, the impression is one of a richness and ubiquity, and that I think is a feeling within exoplanets that's shared. So what are these 3 main ideas? If I only have your attention for 14 minutes, what would I like you to leave this talk with an impression of? The first is what's possible with studies of individual exoplanets now, but moreover, we've shifted as a field from a log number of planets of maybe 2, base 10, to a log number of 3 or 4, and what has that meant for us? What's enabled that? Secondly, what is the most common type of host star? What does that mean for the ubiquity of planets in the Milky Way? And thirdly, what is the view we're taking right now toward full exoplanetary systems? So how have we transitioned from a field looking at individual planets to their systems as a whole, the context in which they form? So starting with the era of individual planets, there's 2 times in this talk that I'll return to our own solar system to contextualize. This is a movie taken of the transit of Venus in 2012 from NASA's Solar Dynamics Observatory, and yet you can see that Venus passing in front of our host star isn't the only dynamic piece of this movie. You can also see a hint of our sun's rotation. This movie is sped up so that the 13-hour transit of Venus happens in only a few seconds, and also something of the roiling surface of our own star. And yet, if you collapsed all of this beautiful resolution to a single pixel and you were removed to infinity, you still could infer the presence of Venus from the periodic dimming of the star due to the planet blocking some of the light. This method, called the transit method, did not used to be the method by which we'd found the most exoplanets, but it is today. And it's because of a singular NASA mission called Kepler, which was launched in 2009. The mission is easy to describe. It was basically a single silicon eye, and it affixed its gaze on a part of the sky which is about the size of your outstretched hand, held at the end of your arm. It's overhead around midnight in the middle of the summer. And it was looking for this telltale signature of dimming when planets would cross the face of their host stars. And to that end, it was looking about 150,000 stars. This was the sum total of knowledge we had about the presence of transiting exoplanets in this part of the sky prior to the launch of Kepler. There was a single planet, which you can see in sort of the top right, called TRES 2, that had been discovered from the ground. And in 2013, this was the total number of planets that Kepler had discovered, and I'll draw your attention to two things. The first is that the red dots, which correspond to things which are approximately the size of Jupiter and larger, are actually relatively rare. These were the only things we were really sensitive to from the ground prior to the launch of Kepler, and we inferred at that point maybe a pessimistic number, which was about 1% of stars like the Sun host a planet like that, a Jupiter, in a few-day orbital period. But what you can see is that these were the lowest of the low-hanging fruit. And all of these delicious planets were just outside of the reach of what was possible from the ground. And the second thing I'll emphasize about this figure is that most of those dots are actually intermediate in size between the Earth and Neptune, 4 times the radius of the Earth. My colleague Leslie Rogers likes to say these are 80% of the planets in the Milky Way, and yet 0% of the planets in the solar system. So to kind of showcase what's possible with an exquisite photometer like Kepler, a mission measuring the brightness of stars, this is probably the last single planet paper that I'll ever lead. And I don't find individual planet discoveries as tasty as I once did. And so just to point out what's possible in exoplanets right now, this is showing the actual data from Kepler for this star. So those individual dots correspond to brightness measurements. When the planet passes in front of the star, you see this decrement appear. Because this particular star was so bright, because the planet transited every few days, we saw 218 times this planet pass in front of the star, and so those transit signals have been folded on top of one another. What we were able to discern at the end of the Kepler mission was that every time this planet, Kepler 93b, passes in front of its host star, it prevents 218 photons per million from reaching the Kepler detector, plus or minus 1 photon. And our ability to measure the extent of the planet doesn't only depend on our ability to measure the transit depth. This is a relative brightness measurement. But that Kepler light curve also encoded information about the pulsations of the star that enabled us to determine the relative size of the star in addition to the size of the planet. We were able to measure the size of the star from the astroseismic signals to plus or minus 1%. Because we knew the transit light curve so finely, that translated to a measurement on the extent of the planet of about 120 kilometers aside, a 1% measurement. And this is about our understanding on the extent of an Earth-sized planet. Kepler 93b is 1.5 times the radius of the Earth, which is similar to our precision to measure our own planet only a few hundred years ago. It was the Persian scholar al-Biruni who first measured the size of Earth with precision like this in very recent human history. So to what end studies like this, only after a several-year radial velocity campaign looking at the motion of the star relative to Earth to see the gravitational tug of the planet, were we able to place Kepler 93 on this mass radius diagram. This whole part of mass radius space, where Neptune would be approximately at the ceiling, and Earth and Venus are at the bottom left-hand corner of this mass radius plot, this whole swath of parameter space is unknown to us from bodies in the solar system. It's one way that exoplanets comprise a unique laboratory for understanding planetary physics. From this really long radial velocity campaign, coupled with our fine radius measurement from Kepler, we placed Kepler 93 on this line that my colleague Courtney Dressing showed is a common recipe, seems to be a more or less common recipe for rocky planets smaller than 1.5 times the radius of the Earth in the Milky Way. And yet, the most common type of star is not a star like the Sun. I've shown what's possible for a single planet with Kepler, but I think the main impression that folks in exoplanets are left with from Kepler isn't an impression of single planets at all. This is the sum total of about half of the knowledge we had about the presence of transiting planets in the Milky Way prior to the launch of Kepler. This is a diagram showing them relatively to size with the transit light curves underneath and the relative sizes of host stars and the planets crossing them shown. You can see these are all things which are approximately the size of the Sun, with the exception of the bottom right thing, the one known transiting M-dwarf planet, GJ436, in 2008. It was the single known hot Neptune prior to the launch of Kepler. And this is the sum total of our knowledge with the same diagram, individual schematics of stars and their planets, at the end of the Kepler mission in 2013. But what I want to draw your attention to is that the relative size of Jupiter transiting the Sun would be about 2/3 or 3/4 of the way up that diagram, which is ordered by the relative size of the star. What that means is most of the stars around which Kepler detected a planet are smaller than the Sun. And that's true even though these planets are easier to see around smaller stars. So even with that selection bias, what we found is that small planets especially seem to be a factor of between 2 and 10, depending on the relative size of the planet you're talking about, more common around small stars than they are around Sun-like stars. And the reason why this is especially interesting is because these small stars themselves are the most ubiquitous type of star in the Milky Way. So I'm showing here a schematic comparing two sort of typical planetary systems in the Milky Way as we understand them now. Our most familiar planetary system on the left, and Kepler 186, uncovered by Elisa Quintana. And this is showing a top-down view of those two types of planetary systems. The green is showing the relative so-called habitable zone. Because these stars are so much smaller, planets have to huddle much closer in so that water can be in its liquid form. And you can see with broad strokes, these planetary systems are not dissimilar. Kepler 186 hosts at least 5 planets by virtue of the fact that we see all 5 transit. At least one of them resides in its star's habitable zone. And these planets are all relatively coplanar. So that's sort of a model for a typical type of planetary system in the Milky Way. Because M dwarfs are 75% of the stars in the Milky Way, and each one hosts on average between 2 and 3 planets. This is at least between 200 and 500 billion planets in the Milky Way alone, and the vast majority of those, if they're rocky, the conditions under which life might potentially evolve are very different than the conditions that nourish the evolution of life on Earth, by virtue of the fact that their host stars being very different. So I'll close with 2 things. First, a view toward full exoplanetary systems, and then a moment or two spent on where we're going next. What is the NASA mission that follows on Kepler's legacy? So for the second time in this talk, I'll return to our model of the solar system. So we are, compared to Kepler 186, not dissimilar. We have at least 8 planets, depending on how you do your accounting. And they're almost coplanar with one another. The largest degree of misinclination with planets in the solar system is only 7 degrees. And plotting all those mutual inclinations in a histogram, it would peak at around 2 degrees. We're very coplanar. So now let's zoom in interior to the orbit of Mars, the terrestrial planets. And this is showing a top-down view of their relative orbital separations from our star. And on the right is just a bouquet of the multi-transiting systems, among which Kepler 186 numbers, that were discovered by Kepler by virtue of the fact that the systems are so flat that multiple planets are seen to transit. What we now know is that the Kepler 186 model, where you have at least 5 planets per star, and those planets are very coplanar, is around at least 20% of these really small stars. And we think those are conditions which, at least in their orbital properties, are similar to the solar system, circular orbits and relatively stable. So where are we going next? It is very exciting for me to be able to say we've detected the first system of planets around an M dwarf, multiple system of planets around an M dwarf, with the next NASA mission to follow on Kepler, which is the TESS mission. It was launched only a few months ago. And unlike Kepler, which looked at a single patch of the sky and didn't blink for 4 years, the average distance to those stars is hundreds of light years away. TESS has a very different strategy. It's looking for the planets around the nearest stars now that we know they must be there from the demographic understanding we have from Kepler. So we're sort of in the middle of this third orange slice right now from TESS. It's doing the southern hemisphere first, and then it'll flip around and do the northern hemisphere. And I want to show a depiction of what we predict will be the number and relative distance to Earth of the TESS detected planets. So tiling the whole sky, performing a year, looking at the southern hemisphere first and then the northern hemisphere. And this video, which I'll, thank you. is made by colleague Zach Berda. So this is showing zooming out with the Earth and the solar system at the center, where the predicted locations will be of the planets uncovered by TESS. So the blue planets correspond to things that Kepler saw in contrast. You can see how they reside in a single part of the sky. The TESS planets are going to be much closer, something like 1,200 planets within 100 parsecs, or 300 light years, by virtue of the fact that most of the nearby stars are M dwarfs. And I think it's something that behooves us within exoplanets to think about as the type of science which it's possible to extract, not only with exquisite studies of single planets, but also what types of studies are possible with hundreds and thousands. Thank you. I'll close there.
So we have time for a question or two. Please, if you have a question, go to the mic. The session is being recorded and shown online, and that's the only way people online would be able to hear the questions.
Do you know if the solar plane of those exoplanets is in the same plane as ours?
It is by virtue of the fact that we see the planets transit, so they're in the same line of sight as the Kepler telescope. They have to be, but they're oriented, so the direction that they're oriented has to be so that Kepler is aligned with them, but I forget how, relatively speaking, that compares the Kepler axis at which it observed with the ecliptic of the solar system. Yeah, the question is, like, would these planets also see us transit? And I'm not sure.
We have time for maybe one more short question.
Hello, Dr. Ballard. Would you expect the planet demographics in a solar neighborhood to be very different from the Kepler sample? Thank you.
I would expect them to be different from the Kepler sample by virtue of the fact that we're looking at a different set of stars. So what the TESS mission will see will be affected by the budget, relatively speaking, of different spectral types that go into the population of stars we're examining. So because Kepler wasn't really looking, it wasn't a volume-limited sample. It focused upon addressing the science driver, which was the frequency of Earth-sized planets orbiting sun-like stars. It looked mostly at sun-like stars and only at a tiny handful of planets smaller than half the radius of the Earth. So I think it looked at around 5,000 out of the 150,000 total budget of stars that it looked at, whereas TESS will be looking at more M dwarfs than anything. So it will produce a different yield of planets around different types of stars. But as far as the underlying demographics of planets that are being plumbed by both missions, my instinct is that they're similar, because even though planet formation is a function of metallicity, the relative metal content of stars, it doesn't really get that different until you get like 100 parsecs or more out of the plane of the Milky Way galaxy, so 300 light years or something. And Kepler was still sort of within that disk, within the disk of the Milky Way. So my guess is that it won't be different. Generally speaking, but I'd be happy to be wrong, because then I would know the answer.
Thank you. We're going to have to move on to the next talk. So our next speaker is Amy Simon, who will be speaking about our solar system's giant planets as exoplanet atmospheric laboratories.
Okay, well, we'll just struggle through with the difficulties here. What can I tell you? Solar system's hard. So I'm going to talk to you about using our giant planets to help us understand the exoplanets, and actually it works in both directions. So, this is not just solar system centric. We learn quite a lot from each other. And so I've got two main things to discuss. One is looking at which physics applies and how we can learn something from sparsely sampled data sets. So this comes down to, why do our four giant planets look so different from each other, even though in theory, they're made of almost the same stuff. What can that tell us about these unresolved planets? Let me just put the other point up. And then the second would be, what can this tell us about solar system formation? And this is where they kind of tie back to also understanding each other. Okay, well, that's a perspective issue. I think it's a Mac PC thing. when in doubt.
No, it's both. It's through an AV system. It's not the computer, it's the AV system. Okay, I think we're going to just continue for now.
Yeah, we can just,
Yeah.
we'll keep going and see how this works. So here's our squished planets. The idea here being, look at how different our 4 planets look from each other. Jupiter to Saturn, Uranus to Neptune, they're different colors. You can see different amounts of structure. You can see differences in storms and clouds. Why are they so different? And there's a few possible reasons for this, and one of them, of course, is the fact they're at different distances from the sun. They have different tilts. They have different seasons. They are not the same planets. So we're seeing quite a difference just from those things alone. If you look at the difference between Jupiter and Saturn, part of the reason that Saturn is so much more hazy is the fact that it is a little bit colder than Jupiter. So those clouds are suppressed down below haze. If you look to Uranus and Neptune, you're seeing the fact that they're so much colder, you have different dominant gases. So the clouds are no longer ammonia, they're more likely to be methane and hydrogen sulfide. So you see these differences in color alone just from the fact that they're at different distances from the sun. But that's not where it stops. This is where it gets weird. So we have these different cloud layers. They get extended down, they get pushed down farther as you go out to colder distances. But when we actually look at the differences in the energy budgets of the planets, it no longer makes any sense. So at any particular wavelength, about 45 to 50% of the sunlight is reflected off. That actually turns out to be about 80% of the total energy coming in. When we look at the total energy budgets, so how much heat is coming back off, we don't have a constant amount with each planet. As a matter of fact, Uranus seems to be too cold. And so Uranus is always going to be our outlier. It's our oddball. It's the hard one to explain. It's over on its side, and it's too cold. So if Jupiter and Saturn were one set of class of planets, and Uranus and Neptune were another, you would expect Jupiter and Saturn to pretty much be the same, and Uranus and Neptune to be the same. Well, they're not. Neptune gives off almost as much heat as it's absorbing, whereas Uranus gives off quite a bit less. So this is a kind of mystery trying to figure out why they don't do the same thing. Okay, so we have more internal heat at Neptune than Uranus. What about the winds? Well, that also gets weird. The winds at Saturn are much higher than the winds at Jupiter. The winds at Neptune and Uranus are also much higher than Jupiter. So they're clearly not being driven by solar radiation. Some of this is coming from that internal heat, which is quite different from planet to planet. And so early on in understanding our own solar system, we had to figure out models that put our planets where they are now, explain these differences potentially in composition and also in thermal energy. And if you were at the ice giant session this morning, you would have heard some theories on Uranus and how it got tilted over. And one of the explanations for its low temperature is the fact that when it got tilted over, there was some stirring up from the inside that also potentially changed how it releases its thermal energy. Another theory is composition differences. Difference between Jupiter and Saturn, Uranus, and Neptune, some people think it's slushy and icy on the inside. Well, we don't know. Okay, we don't know a lot of these things about our own solar system. So when we go to extrapolate this to extrasolar planets where we have even less data, it becomes even more of a challenge. And so it's something we have to be a little careful about. Okay, so we don't know that. Well, do we know what they're made of? Let's look at composition from spectra. The early spectra of the outer planets, you'll see their spectra are solar reflection, but you have absorption bands from ammonia and methane. So you'd be forgiven if early on you thought Jupiter had floating spherical cows, because that's what we saw. We saw a lot of methane and not much else. In reality, of course, we know that's not true. But there are a lot of methane absorption lines. It turns out even very tiny trace amounts of methane can have a big change on the spectrum. Well, the reality is once we could see the hydrogen collision-induced absorption bands, it proved the fact that, of course, these planets are predominantly hydrogen and helium. Now, helium you can't see. So when you're trying to understand what the composition of a planet is, you have to be a little careful about over-interpreting absorption bands because they're only telling you part of the story. Okay, so surely we can at least figure out the rotation of these planets, right? Well, we actually used Kepler to look at Neptune as if it were an exoplanet. And the reason we were doing this was hoping to see the actual oscillations of Neptune, its spherical harmonics, the breathing modes, that would tell us actually something about the internal structure. So we looked at it over a very long time period, at very high resolution, high cadence, and because of that precision photometry, we could get this fabulous light curve. Well, you can see that light curve is awfully variable. If you lay any particular days on top of each other, it's a mess. So can we pull out the rotation period of Neptune? Well, not really. What we can pull out is the rotation period of the clouds in Neptune's atmosphere. You don't ever actually get Neptune's actual rotation period, and that's because those clouds are moving at 300 meters per second, different than the rotation period. And so if you tried to figure out the rotation period of Neptune, you'd be off by 300 meters per second. Okay, so, well, what about these oscillations? Well, it turns out with the high precision photometry, it wasn't quite enough to get Neptune oscillations. That was just below the noise limit, but we could get solar oscillations. Okay, so we can learn something about the parent star, right? Well, we used the standard mass-radius relationship based on the oscillation frequency, and we predicted a value for the sun that's about 10% too big. So you have to be careful with your data. There are some little nuances to this. It turns out that the sun's oscillation period has some variability as well. And so if you're looking at an extreme, you will get the wrong mass and radius for the sun. So using any of these methods, you just have to be careful to understand your data. And of course, the more data, the better. So what can we figure out from all this then about how they formed? Early on, we had these nice models of the solar system. Everything was where it belongs, no problems. And then you guys found exoplanets, and we had these giant Jupiters too close to their parent stars. And this caused all sorts of problems. Why are our giant planets not in close to the parent star? And we started looking at these different methods of forming our solar system, and the idea came up that our giant planets probably did migrate inwards. And if we didn't have a Saturn, a Uranus, and Neptune, Jupiter would have swept up everything in the inner solar system. So by virtue of having multiple giant planets, it was able to pull Jupiter back out where it belongs. And so that's this grand tack model, where we pull, basically like tack on a ship, you pull that Jupiter right back out. And so that's another scenario to put everything where it belongs. Then we get into late heavy bombardment, and we move all the little bodies around. So even just understanding where our own giant planets are is problematic. Which of these models is right? There are ways to figure this out. And one of these is to look at the noble gases, which do not change over time. They don't react in any way. So wherever they were when they formed is what they should be, and also the isotopes of some of these different elements. And that's something we just don't know very well, even about our own planets. And this is why it's problematic to apply any of these models to our own solar system, because we just don't actually know how old or where our planets formed. And so there's a variety of different models out there. They formed in place, they migrated, grand tack, jumping Jupiter, all sorts of craziness. But the short answer is until we get these measurements, we won't know exactly which parts of our models of our own solar system are correct. And so by having these extrasolar planet systems, it actually told us, do we really understand our own? And the short answer is no, not yet. So this is an area that's still under exploration. So how can we do this? The noble gases are one of the keys. When we looked at the Galileo probe measurements of Jupiter, we found helium and neon depletion. And the idea is there's helium that rains out. And that's one theory for where the helium goes on Jupiter. Well, we expect it to be even worse on Saturn. And what does that mean? Well, depending on what happens with the helium, if it rains out, it changes the temperature profile of Saturn. And so without it, Saturn cools too fast. With it, you can extend it out so it formed at the right time in the right place and is where it should be now in terms of temperature. And so these are one of the things we look at when we're trying to figure this out. The other thing that can change this is internal structure. And so this problem with Uranus, where the heat's not coming out, or presumably isn't coming out, it could be that convection is inhibited. So these planets have convective areas, they have radiative areas, and how easily the heat can get out to radiate to space is part of this whole problem. So you can see there's a whole variety of things we need to understand. And so let's go back to Uranus. Was the measurement correct? We have one data point. So you always have to be a little careful about interpreting one data point. So really, this is one of the reasons we need to go back to these planets, is to actually get better thermal measurements and do these in situ measurements of the noble gases, because that will tell us how old the planets are and then where they formed. So what do we know now? Well, we have these models of the interior of Jupiter and Saturn, Uranus and Neptune. There's a lot more water in Uranus and Neptune, we think, whereas there's mostly the molecular hydrogen and helium in Saturn and Jupiter. But again, we don't have a lot of data. That's the data we have. You can see it's a little sparse up at the top there for Uranus and Neptune. We have quite a lot for Jupiter, and this is because we had the Galileo probe. So this is really the key to having the in situ measurements in our outer planets, is the fact that you can fill in what are the abundances of the noble gases, and then of course the main bulk elements and their isotopes. Because this is going to fill in whether or not we have this interior structure correct, and again, the age and location where they formed. So what are the big science questions we're still looking at in planetary, in particular with our decadal? One of them is, do all these planetary systems form the same way? Why are the ice giants different than the gas giants and from each other? And it's not just how far they are from the sun. Can these remote observations, including these single data points, actually give us accurate information, particularly below the clouds where we can't see? And so some of this is looking at, are there new novel ways we can use remote measurements to get to some of this information? So the things we need are, of course, the in situ measurements. You can't get the noble gases any other way. There's ways to attempt to get to the helium, but that's it. You can't get to the other noble gases. We need the in situ temperature and wind profiles, the cloud layers. That tells us more about, again, how much of that internal heat can get out. And we can look from the outside, but really having that ground truth is critical to making sure we're doing it right. And then lastly, the remote measurements. What can we do to understand the interior layering, particularly at Uranus and Neptune? You can do gravity measurements, a close orbiter that can try to see if there's icy shells in there, for example. We can look at the thermal measurements. And there's also other unique ways that people are starting to look at. One is Doppler imaging, actually looking at the changes in the planet to determine if there's a core and what the layering looks like. So there's a lot that can be done, but this is stuff still in progress. So going forward, and this is primary in the planetary decadal as well, we need to do atmospheric probes at all 4 planets. But we also need these long-duration, high-cadence observations. Things like Kepler were really valuable for looking at Neptune. We've also looked at Uranus, which turns out to be a little tougher because it doesn't have a lot of variation. So we're learning a lot, even using the astrophysical platforms to look at our solar system. And so this is the sort of things we're going to be looking at going forward as well. So hopefully we can use this to inform both our solar system and the exoplanets. Thank you.
So is there a question? And if you have one, please go to the microphone.
I wanted to ask this question of the previous speaker, but obviously you can answer it as well. The new mission, TESS, is going to be looking at many different directions. Does that mean that it will have to take a much longer time to identify the frequency of these transits and so on? And I mean, Kepler was always pointing in the same direction, and I think you have to look at these planets for a very, very long time to see what's going on.
Yeah, I don't know what the time period how long it's going to sit on a particular field for TESS, but you're right, and particularly having multiple transits makes a big difference because those little subtle variations can cause quite a lot of error. Even with 90 days of Kepler looking at Neptune, it is tough to get a signal out. So yeah, I'm not sure what the cadence is for TESS, but you're right. Being able to go back to fields again, for example, maybe in an extended mission could be quite valuable.
All right, thank you. So our next speaker is Eric Lopez, and the title of the talk is Understanding Hot Neptunes in the Era of Exoplanet Transit Surveys.
There we go. Just play.
All right, well, thank you very much. Thank you all for coming. Thank you for inviting me to talk. And a huge thank you to Sarah and Amy for that fantastic lead-in. Because what I really want to, in these brief couple minutes, talk about are some of the lessons that we've learned from the Kepler mission about these new exciting exoplanet populations and how those might be complementary with what we've learned about the giant planets in the outer solar system. And also, of course, a huge thank you to the Kepler mission, which is really what's has made all of this science possible, and actually has just finished its extended K2 mission a few weeks ago. Okay, so let's play a quick little game. Solar system planets versus exoplanets. What sort of information can we get to play around with? Well, the first question is, okay, how about just are the planets there? Orbits, radii, masses. And even that last one, masses, is often extremely difficult. That's where a lot of the follow-up effort in the exoplanet community goes. But most of the time, if we're lucky, this is the information we have. You know, in some sense, the exoplanet community is in the 19th century. You know, we're in the era of Kepler, essentially. Meanwhile, you know, there are all the other bits of information that you can get to try and learn about a planet's interior in the solar system. Some of these are sometimes possible with intense observing time. Things like trying to measure the thermal emission and the rotation rates. For some planets, maybe if you get a lot of observing time, things like magnetic fields have not been observed yet. Maybe this might be possible in the future with things like the SKA, but thus far we have no information. Things like the gravitational moments and all the things we're learning about Jupiter from Juno, generally speaking, cannot be done. And of course, in situ measurements are not happening anytime soon. But statistics. This is the killer app for exoplanet science. You know, of course, in the solar system, we have 8. If we're here, we're talking about the gas-rich planets, or really 4. As of yesterday, the official NASA count of confirmed planets was just under 4,000. And the thing I really want to emphasize here, when we talk about why we're so excited about these statistics, this isn't just about stamp collecting. There are lessons you can learn from the statistical properties of these planet distributions. There are features that emerge that can yield unique insights into planet formation, composition, and evolution that you can't get any other way without having that large ensemble population. Oh, and just the thing I wanted to emphasize, so it's not versus, it's an and. It's combining that statistics and the detailed information we can get about solar system. I mean, that's the whole reason we're all here. Okay, so this is, I think, the real starting point for all of the questions that I have been interested in over about the last decade. This is the results of the Kepler mission. This is, as a result of Kepler, we had for the first time an idea of how common different sizes of planets are. So this is from about halfway through the Kepler mission, but already you can see this clear trend that small planets are incredibly common. And one thing I want to emphasize is that it's not just that small planets are common. If you notice, this is planets with orbital periods less than 85 days. That's comparable to the orbit of Mercury. So as Sarah mentioned earlier, if you were to ask, what is the typical exoplanet? The typical exoplanet is a planet between 2 and 4 Earth radii with an orbital period around its host star less than that of Mercury's around the sun. And of course, we don't have any planets like that in our solar system. You know, we have at least one nice example of what an Earth-like planet could be. We also have Venus, we have Mars. We have Uranus and Neptune, but for this intermediate population that is so abundant, we know nothing. We know from follow-up studies that somewhere at about 1.5 times the size of the Earth, there seems to be a transition from a predominantly rocky, by which I mean planets are dominated by rock and iron, like the planets of the inner solar system, to a population that has some large volatile component. And we're not seeing a bare rocky surface. There's something that is lowering their bulk densities. If we go to one of these planet mass radius diagrams, we can see this population is actually incredibly rich. So again, at the bottom left, we have things like Earth and Venus, and then we have this population of planets that seem to have similar bulk compositions. Things that might be close to the Earth is about 2/3 silicate mantle, 1/3 iron core. We seem to find a lot of planets like that. But we also, in between there and Neptune, there's this abundant population of planets that have some sort of a volatile gaseous envelope. Now, one interesting thing you'll notice, a planet that's 3 Earth radii, it could actually have very different possibilities for its composition. It could be a planet whose mass is dominated by water and other volatile ices, like at least our conventional story for Uranus and Neptune. But it could also be something completely different. It could be a planet whose mass is almost entirely in an Earth-like silicate core, but just has 1% of its mass in a primordial hydrogen-dominated envelope, an envelope more like the composition of the atmospheres of Jupiter and Saturn, but that just was accreted onto that rocky core before the disk dissipated. And interestingly, it doesn't take very much mass. It only takes a few percent of a planet's mass, and all of a sudden you end up with something that is sub-Neptune sized. One of, I think, the most interesting things to come up from follow-up studies in the last couple of years is we've now resolved that radius distribution more finely. And we now know that this population actually appears to be quite bimodal, that there's a gap in the radius distribution in between this mostly rocky and this likely non-rocky population. And in particular, this gap is fascinating. This is one of those statistical features that I was mentioning earlier that is incredibly diagnostic. As this was actually a feature that was predicted by models of atmospheric escape going back about 5 years ago now. And the really fascinating thing is the location of that gap, the radius where it occurs, is highly diagnostic of the bulk composition of the cores of these planets. If you look on the left here, the figure in gray shows the distribution observed by Kepler. The 3 colored curves, meanwhile, show different core compositions. Blue is if you have a core that is pure water, red is a core that's pure iron, gold is a core that's pure silicate. And the thing that you can notice if you just chi by eye for a second is if you add about 1/3 of the pure iron curve and 2/3 of the silicate curve, you do a pretty good job of reproducing the data. However, if you had something that was more like a scaled down ice giant, something that had most of its mass in water, that is strongly excluded. Now, it's not to say these planets couldn't have many Earth oceans of water. It's just saying water is probably not the dominant component of their mass. Now let's go 2D. Let's go into the next dimension. I think one of the main things I want you to take away is that this planet distribution is incredibly information rich. This is not just a scatter plot. So this is showing, again, from those follow-up studies from B.J. Fulton's paper from last year, the joint occurrence rate of planet size versus irradiation relative to that of the Earth. So you have, at small sizes, a population that is likely rocky, and at large sizes, a population that is likely gas-rich. But there's a ton of information in where those populations are, where that gap and the shape of that gap in between them, and where planets aren't. And all of those are features that can teach you something about how these planets form and evolve. One process in particular that I've been interested in for a long time is how these planets might be affected by extreme atmospheric escape. I think there's strong evidence that some of these gas-rich planets, these hot Neptunes, may lose their entire gaseous inventory and end up becoming stripped rocky cores, more similar in density to planets like the Earth. This is actually not an idea that is new to exoplanets. We've known going all the way back to the 70s and 80s that extreme atmospheric escape in some form probably significantly changed the atmosphere of Venus. And then more recently, this sort of escape has actually been observed happening, initially for hot Jupiters, but more recently for hot Neptunes, where if you look in Lyman alpha, This is for a hot Neptune GJ436b around an M dwarf. You can actually see this large cloud of partially ionized material that is being driven off the planet's atmosphere, in this case, mostly by interactions with extreme UV and X-ray radiation from its host star. One of the, I think, the key lessons for the exoplanet population is that either that process or something similar to it has probably played a major role in sculpting the population that we find. And maybe this isn't that surprising. As I said earlier, we're talking about planets that are closer to their star than Mercury is the sun. In fact, typically, most of these planets are orbital periods of about 10 days or less. So these are in an intense environment. They're receiving huge bombardment of irradiation, X-rays, EUV, coronae, and additionally, people have also suggested giant impacts that can drive off large amounts of material. All of these processes may play a role. Just as one example, although, of trying to convince you that these sorts of processes probably have had a huge impact, this is a diagram that I like to use to diagnose the role of extreme atmospheric escape. On the left is on the y-axis is the total lifetime irradiation in ionizing radiation that a planet receives from when it forms at about 10 million years to its current age. The x-axis is the planet's binding energy, and you'll notice planets seem to pile up at this sort of threshold here. There are a couple planets that lie above it, but those are stripped rocky planets. Those are these burnt out magma planets that probably have lost whatever primordial atmosphere they initially have. Whereas meanwhile, if you put on a simple analytic model of these sorts of atmospheric escape processes, you can see clearly planets are piling up here. Something has affected these planets. So if we go back to this 2D distribution and let me throw some theorist labels on it, I would say, okay, we probably have a rocky population, a non-rocky population. We have a region at highly irradiated orbits where we find rocky planets, but we do not find non-rocky planets. That may be a signature of these atmospheric escape processes. We also have this gap in between the two populations, which I haven't had time to explain how that gap originates, but it is also a natural outcome of these sorts of escape processes. And I think this is, in my mind, one of the real legacies of the Kepler mission, and one of the ways we are going to continue to move forward. Analyzing the Kepler data, the K2 data, and the test data is there is a huge wealth of statistical studies still to be done on these. This is just one example from earlier this year that I found particularly fascinating. This is fitting for that transition between the rocky and non-rocky planets, that radius gap. This is trying to fit the slope of its period dependence. And you can see this study strongly excluded a flat line, that they find there is a period dependence. And interestingly, this period dependence is what you might predict if all of the rocky planets Kepler found, if that entire population were just stripped hot Neptunes. So that's saying that may be the dominant way, at least the rocky planets we found so far, they may actually be, in large part, a population shaped by these sorts of processes. Okay. So, a couple key takeaway messages. These small, short-period planets are incredibly common. And by studying the demographics, by studying the statistical properties of these planets, we can learn about their bulk compositions, their formation, and their evolution. At least around sun-like stars, these planets seem to be relatively poor in water and other volatile ices, with roughly Earth composition cores. But you also have many of these planets that have retained these likely primordial gaseous envelopes. Atmospheric escape has probably played a major role in shaping these populations. This is, again, because these are a very different regime than the giant planets in the solar system. But going forward, I think TESS is really going to be the game changer. With TESS, we'll be able to understand the full multi-dimensional parameter space with the thing that I mostly didn't talk about is mass as the extra dimension. And that's going to be, I think, a huge wealth of information from all of the follow-up. Okay.
Thank you. So our first question is going to be a question that came online.
All right, so it's how strongly is the transit period correlated with distance from the star?
Well, I mean, it's just Kepler's law, so it's exactly the same. So it's period squared goes as semi-major axis cubed.
All right, we have time for one more question. If you have a question, please go to the microphone.
Can I just yell in here?
No, because
The people online won't be able to hear you.
So about the magnetic field of the exoplanets, is there anything that Zeeman splitting in the spectral signatures can tell us about the exoplanet magnetic fields?
I know, I've talked to helium people that have suggested that. The problem is you're dealing with things that are so much fainter. It's about, when you're trying to detect a planet's atmospheric signature, you're often talking about a 1% signal on top of a 1% signal, and that's just for the bulk planet's atmosphere. I think Zeeman splitting, I'm not an expert. My understanding would be quite difficult. My sense is a more promising area is to look for auroral emission. That with things like the SKA, you might be able to see signatures of that in the future.
All right, thank you. We're going to have to move on to our next speaker. So our next talk is going to be given by Wendy Pinero, and the title is Planetary Interiors as a Control for Habitability.
Hello, thank you for being here. Today I'm going to talk about, shift topics a little bit. I'm a geophysicist, and so we're bringing together astronomers and geophysicists to really start to explore our wider galaxy and the likelihood of life. Habitability, we know from our Goldilocks story is a function of being in the habitable, an appropriate distance from your sun, not too hot, not too cold. However, it's controlled by far more than just being not too hot and not too cold. We need to have the right materials for life. We need to have nutrients in our water. We need to have a stable climate system. And in fact, a lot of these things are controlled by the interiors of the planets. And I want to start to leverage some of the statistics that we have of exoplanets, much like we've heard in the previous talks, to try and see what we can say about how variable the interiors of planets are and what impact it may have on the fate of a dynamic planet. So I'm going to start with one of the things that we can really observe, and that is that there's a significant variation in the relative abundances of silicon, magnesium, and iron in the stars that are hosting planets. And so this is an array of sun-like stars, not necessarily hosting planets themselves or discovered or observed planets at least, but we can see that there's factors of 5 variation in the ratio of these elements between these stars. And these are the environments in which these planets are forming. Together with oxygen, these are the 4 most abundant elements in the Earth. And so why might I think there might be some relationship and something that we can say about the composition of these stars and the compositions of these planets is that, in fact, when we go back and look at our solar system, the composition of the Earth is very similar to the composition of the star, in particular with regards to those elements that tend to condense at the highest temperatures: iron, magnesium, and silicon. There's variations. There's a lot that we don't know about how our solar system formed and evolved. It was a highly energetic process. Chemistry was involved. There's things that we don't know. But we do see that for the Earth, we see variations that are less than the variations that we see in the stars from which these form. We've heard a couple of times today that the iron fraction of the planet is about 33%, which happens to be about what it is in the Earth. Is that, in fact, a general law? Or is it something that maybe will vary between these planets? This is a multidisciplinary session, and I've been asked to refrain from using very much jargon, but we've already heard some places where the jargon actually has been in conflict. So I want to be super clear. I'm going to talk about rocky planets. That is, when it transits in front of its star, the size planet that we see is made up of an iron-nickel core. So this is the Earth definition of core, that is overlaid by a silicate, an oxide mixture of, this is the rock part of the planet. Together, this is in the previous talk, what we were hearing was the core of a planet. So I'm using the Earth science definition. The boundary between that core and the mantle, in geophysics, we call it the core mantle boundary, CMB. Astrophysicists, it is not the cosmic microwave background. I did a sabbatical in an astronomy department. It took me about 2 months to figure out what everybody else was talking about because of this misunderstanding. I'm also going to be talking about water worlds. We think of the Earth as a water world. It's the blue planet. It's the pale blue dot. I'm going to define a water world as something where there's a layer of water, be it solid, liquid, gaseous, on the surface, such that it has a measurable effect on the size of the planet. So by that definition, the Earth is a rocky planet, but not a water world. All right, so let's come back to this. And we have this sense that there's a variation in the star compositions, that the Earth and the solar system, terrestrial rocky bodies, reflect the composition of our star. Wouldn't it be great if we could test this hypothesis? We now have a huge amount of statistics. We have a lot of planets. Can we test, in fact, whether or not these planets are forming with a composition that reflects the composition of the star? And so we can go back to this, and if I just make the a priori assumption that stars have condense exactly the refractory elements in the abundances that we expect, that we see in their star, we can see that from this these stellar abundances, that for the core fraction should vary from something that's maybe less than 20% of the mass of the core, so the core mass fraction is less than 20%, to over 50%. Iron has a much greater density than that of rock, and this difference ought to be measurable. If we look at that 1.5 Earth radius, kind of the largest planets that we think might be rocky, this means that the masses of these planets will vary from less than 4 Earth times Earth mass to more than 5 times Earth mass. That is more than a 25% change in the mass of the planet, and this is becoming something that we should be able to begin to measure soon. Was that enough caveats? I hope. Okay, so we've seen this in a variety of different ways already today. The radius of planets in multiples of that of the Earth, and the mass, this is cut off, sorry, in multiples of the Earth's mass. And we see, in fact, the big problem is that there's large uncertainties in the masses, and in particular the mass, but also some significant uncertainty in the size of these planets as well. I'm going to look at today a suite of a few planets that have uncertainties that are below that range, that 25% range, that have uncertainties in mass that are under 20% and uncertainties in radius that are under about 4%. And I would like to say that gives us a variation and a measure of the uncertainty in the mean density of that planet. And so if I start with the assumption that all of these planets, and in fact we're fairly certain that not all of them are, but if we do start with the assumption that these planets are rocky, I ought to be able to predict the relative proportion of core and mass, the core mass of the planet as a function of the uncertainty. So let me walk you through this. So that I'm taking the a priori assumption of a rocky planet, and if I assume that I have the uncertainty in mass as measured for these planets with the same symbols as before, and the uncertainty in radius with the same symbols as before, there is an uncertainty in what fraction of that planet is core. And so this is a core mass fraction uncertainty. So when we're talking about something like a 20%, this curve here, a 20% uncertainty in the core mass fraction, this is around a nominal Earth fraction. And so this is a plus or minus 6% mass, core mass fraction. And I highlight the 20% curve because if we start looking at carefully selected bright targets of tests, I understand from colleagues that with quite a bit of diligence, with some observation, with long time observations, we ought to be able to start to get some masses down to a precision of something closer to 5 to 6%, and planet radius precisions down to 1 to 2%. So I'm looking at this hypothesis testing approach. I want to look at the composition of the star. So I have variations in the compositions of the star, and I can go the other direction. I can predict what is the relative fraction of that planet that I expect to be core relative to mantle. And I can then measure the mean radius and mass of the planet, and should what we actually measure of the expected density be greater than what we would predict based on the composition of the star, then we're going to be up on this side of the graph where this ratio is greater than 1. And this is the situation that we've got with Mercury. Mercury's got more core relative to mantle than we would expect it to. Going in the other direction, if our planet turns out to be less dense than we would expect, then this is something that I'm going to assume is something like a water world or a puffy planet or a gassy planet. Taking some of those planets that I highlighted before, where we have compositions of the stars, we have masses and radii, we can then plot this on this graph, plot them on these graphs, and most of these are in fact coming out into this water world realm of things. Or there's something else going on such that they're forming with less core than we would expect them to. The one exception here is something that is kind of with error bars crossing the null result here. However, with the test, we should be able to get at least a few planets that get us down into a realm where we ought to be able to distinguish something from more than 3% water or from having lost maybe more than 20% of its mantle. All right, now I want to get into kind of this realm of habitability and get to be far more speculative. And the surface to interior recycling is something that a lot of talks yesterday talked about the carbon drawdown and the regulation of carbon in the atmosphere. And this occurs at this water-rock interface where we need to have fresh rock brought up to the surface through dynamic processes that can then interact with water, carbonic acid in the atmosphere, draw down carbon. And so back to this diagram, instead of looking at the core side of it, I want to look at, after we have variations in silicon to magnesium, as we have mantles that are more silicon rich, they're going to form minerals that contain more silicon into the extreme, pyroxenes and quartz, and then in the more magnesium-rich, we end up in the extremes of olivine and pyroxenes. Now, if you know something about the material properties of these materials, we start to see variations in the strength of the materials, so leading to convection in the interior. We see variations in how much water they can store in terms of softening the Earth's interior. We also see variations in the petrologic behavior of rocks as they would come up towards the surface and producing partial melt, leading to the crusts that we find at the surface of planets. This is something that is extraordinarily speculative, but I do want to go through some kind of just playing with the information that we can because we have some statistics and what can we learn. And on Earth, we don't understand why we have plate tectonics. But we do know that the rocks at the surface that end up sinking down into the interior because once they get down just a little ways, metamorphic transitions in the rocks lead to a densification, and just through negative buoyancy, they tend to sink downwards. This leads to this ends up enhancing the recycling process that we see on Earth, which can refresh rocks at the surface. A quick calculation, though, of something where I have a silicon-enriched mantle, I end up producing things like andesites. We don't end up with a rock that's ever going to sink down into the interior. So this is going into the realm of like super speculative. I'm not describing any particular planet, but say we support this hypothesis that the composition of the sun and the composition of the planet reflect one another. Say that we understand something about how a planet differentiates. Let's say that the planets differentiate with more or less the same oxygen FO2 that we would expect that reproduces the Earth. And we can start to look at what are the partial melts that form, making new rocks at the surface of the planet. And then let me do this calculation. As I go through the transition into the deep interior, will that rock become more dense? And the question is, will it sink or will it float? I'm going to look at this crossover depth, and I noticed I missed my yellow light. And we're going to look at this crossover depth. And I just want to point out that temperature matters and composition matters. And we end up being able to predict a wide range of behaviors in rocks. I do want, because this is work done by an undergrad, so I want to highlight this quickly. If we start looking at these water planets, is look at the topography of planets that we would expect. There's very limited water that you would expect before you lose the ability to have that water-rock interaction that occurs. This is the condition under which you flood a planet. And flooding of planets, this is a project that we've been calling the Bad Movie Project, of looking at what happens when you completely flood everything. So I will end there.
Time for a question.
Very interesting talk. It's been known for a decade or so, since work by Elkin, Stanton, and Seeger, and more recently by Zhang and Sasloff, that in addition to things like iron and magnesium, the internal structure of a rocky planet depends critically on the oxidation state. And you can have a rocky planet that has the same amount of iron, magnesium, silicon, but is more oxidized, and it won't form a core at all, and the density will be about the same, a few percent lower. So are you making some assumption about the oxygen fugacity?
There are some assumptions about oxidation state that go into those calculations. One thing that I want to point out is if you look at the mineral physics, and if you get to the higher pressures in the interiors of mantles, iron tends to undergo through this auto-redox process where it oxidizes itself and reduces itself to produce free iron, which becomes a core. So there's a lot that we don't know yet about the Earth as to why the Earth acts in the way that it does and the physics of these materials. But if you apply that sort of physics, it's almost FO2 agnostic. You end up producing a core. And so there's one paper that's out there. I didn't highlight it because the work was done on Friday. But the mass and the radius of the planets don't match the highly oxidized planet prediction.
Oh, thank you.
Yeah.
I wanted to make one more mention. You did confuse me earlier in the day with your tweet about the CMB in the session.
Yeah, yeah.
So
I'm
thank you for
glad
clarifying that.
it brought you here. If that's what brought you here, it was worth it.
All right. Do it during panel. I'll ask the question during panel. Thank you. All right, we need to move on. So our next talk and the last freestanding talk will be given by Carolyn Morley, and From Exotic to Familiar, Characterizing the Atmospheres of Extrasolar Worlds.
Okay, great. It's great to be here. This is my very first AGU, so that's been very exciting. One difference I've noticed so far of many differences is that there's beer. There's free beer at the 3:30 coffee break, so I think that's great. I think we should do that too. Okay, so I'm excited to tell you about extrasolar planet atmospheres today, and I think the talks previously in this session have really laid the groundwork for this, that we're in this amazing stage right now where we've gone from just having the 8 planets in our own solar system that we use to try to understand the physics and chemistry of atmospheres to having something like 4,000 exoplanets. And what I want to do is just go from having the demographics of these, which we've learned is already really informative, but actually be able to dive in and look at some of these planets in great detail to figure out what are all of these planets actually like, what do they look like, what are they made of. And so over the next 12 minutes, I'm going to start by telling you how we actually go about observing the atmospheres of planets that are dozens of light years away from the Earth. Then I'm going to give you 2 highlights of what we've learned so far, and then I'm going to look a little bit to the future, because this field in particular in exoplanets is about to really explode in terms of atmosphere observations. So let's start with how we actually do these observations. So the first most obvious way you might think of looking at an exoplanet and looking at its atmosphere is by taking a picture of it and taking a spectrum of it. And so this is an example of where we've actually been able to do this for a planetary system. So this is a system around a star slightly larger than the Sun. And you can see here actually this is over multiple years, and you can see the orbital motion of the planets as they orbit around. And so the trick to doing this is to be able to block out the starlight really well, because in this case the planets are over 1 million times fainter than the star itself. So you need a coronagraph to block out the starlight really well, then these planets emerge, and then we can stick a spectrograph on there and actually measure spectra of these planets. In this case, this is all thermal emission spectra of these planets in the near infrared. We're able to measure the temperatures of the planets. They're all over 1,000 Kelvin. We're able to measure absorption features and detect things like carbon monoxide and water vapor in these atmospheres. And so this technique, which I'm calling imaging with a coronagraph, we've been able to do this for about a dozen planets. They're all giant planets. They're all much larger than Jupiter even. They're all distant from their host star, because we can only do this technique when they're far enough away that we can actually resolve them. And as it turns out, so far, all the planets we've been able to use this imaging technique on are young. And that's because planets are born really hot when they're first formed. We can only see the ones that are really still glowing brightly from that heat of formation. But there's another technique, the second technique I'm going to introduce now, which takes advantage of the fact that many of the planets that we found so far, the majority of the planets we found so far, actually transit in front of and then are eclipsed behind their host star. And so we can measure this to really high precision. We can measure both the transit and the eclipse, and sometimes even the phase curve in between the transit and the eclipse. And we do that not just at one wavelength, we do that spectroscopically, and we can break that light curve into each of the different colors in that spectrum to measure the transit depth and the eclipse depth as a function of wavelength. And so we've been doing this a lot recently with the Hubble Space Telescope, so that's where this data comes from. And then we can plot the wavelength of the observations. This is in the near infrared again, right around where there's a water vapor feature in the atmosphere. So here you can see the emission spectrum on the top, the thermal emission from the planet, and then the transmission spectrum on the bottom. And this was our first strong constraint on the water vapor abundance of a hot Jupiter exoplanet. And so this has really become the workhorse for understanding exoplanet atmospheres so far. In terms of the number of planets we've been able to look at, we've done this now for dozens of Jupiter-sized planets. We've done it for over half dozen Neptune-sized planets and slightly smaller than that. But they're all quite different from the planets in our own solar system, because they're the ones that transits. They're on these short period orbits around their host star. So a lot of these are also quite hot because they're so close to their host star. And it turns out that this technique is easiest to do around smaller stars. And that's because it's easier to do when you have a deep transit depth. And so there's 2 ways to do that. You can either make your planet larger or make your star smaller. So now I want to talk a little bit about what the science highlights of what we've been able to learn so far. So I'm going to give you 2 things here. The first is that we've actually now detected a huge range of different molecules and atoms in the atmospheres of extrasolar planets. So these are the things that we've detected so far. Hopefully I didn't miss somebody's favorite detection so far. And we've actually been able to measure some of these things in a number of different planets. So I'll just give a couple examples here. Water vapor. We're able to see water vapor in most exoplanets until it gets so hot that the water vapor actually dissociates and then we don't see it anymore. So that's the kind of thing we're able to learn at this point about these planets. Another example, the hot topic of the week in exoplanets, there's been, I think, 4 papers this week on this. We've now detected helium for the first time. We can actually see helium escaping from some of these highly irradiated planets. We can actually measure the speed at which it's flowing away from the planets. And so we have much more detailed measurements than if you had asked us just 5 years ago what we're able to do for these systems. And so as I go through these science highlights, I want to also highlight kind of the puzzle pieces that I think Earth and planetary scientists could help us the most with to understand these different things. And so I'll give you 2 things here. One is this atmospheric escape, that we're now starting to have these really detailed measurements of what's going on, both in terms of the demographics, like Eric talked about, but also in terms of these individual objects where we can see helium and other things flowing away from them. And so we're at the point now where we can start to apply really detailed models to be able to understand these kind of hydrodynamic flows. And then the second thing is chemistry. Chemistry is always hard, and as you can see in this list, we have all kinds of different species that are participating in the chemistry here. So for example, HCN on this list is a product of photochemistry in the atmosphere. And so I think starting to apply people's chemical kinetics models that they've been working on for a long time would be really useful to understand what's going on in these systems too. Okay, the second thing I'm going to tell you is that planetary atmospheres, it turns out, are cloudy and hazy. And we see this across a whole range of different planets. So I'll show you an example of what we see here. And so this is a result that came out a couple years ago. This looks at transmission spectra, so when the planet goes in front of the star, of a bunch of different hot Jupiters. So these are, all giant planets. They're all made of roughly the same building blocks. And they're ordered here in their observations from where we see the largest features to where we see either a flat spectrum or a slightly sloped spectrum. So what happens as clouds form is they have opacity across a whole range of different wavelengths, and so they tend to just obscure the molecular features in transmission that we're trying to measure here. And so the punchline here is really that we see for planets that are, roughly the same compositions, they're all relatively hot, kind of 1,000 to 1,700 Kelvin or so, we see this really large range in how much cloud or haze material there is, and we can't really tell from these observations what those clouds are actually made of. But we have some ideas from the chemistry models that we're able to do. So exoplanet clouds are made of all kinds of different things. So they're made of everything from the familiar clouds that we know of and love in our solar system, like water clouds on Earth or ammonia clouds on Jupiter. But then because we have this wider range of temperatures for exoplanets, we also have clouds made of things like sulfides and salts. And then for the hottest planets, the most of these hot Jupiters, we actually think the clouds are going to be things that are refractory, rocky materials on Earth, things like iron, silicates, corundum, forming these dust clouds that enshroud our planets. And so I think there's a ton of work that needs to be done here in terms of understanding these clouds and hazes in greater detail, and I think a lot of that can leverage the studies that have been done in the solar system. So the puzzle pieces here where I think we need the most help is looking at the microphysics of cloud formation. So there's already studies that are starting to use cloud models that have been developed for the solar system and putting the wider, diverse range of exotic clouds that we have in exoplanets into those models. So that's really exciting. And then the second thing, and something that I think particularly pertains to people who've thought a lot about global circulation models on Earth and other planets, is we're just at the stage where we're starting to incorporate clouds and hazes and their radiative feedback and all of that into the 3D climate models that we're running for these exoplanets. And that turns out to be a challenging problem that I think that people studying that in the solar system could help us out a lot with. Okay. So now in the last few minutes, I want to look forwards to what's coming next for the field of exoplanet atmospheres. And so here's my timeline here based on the resources that we'll have to be able to look at planets. So currently we're using facilities like the Hubble Space Telescope, the Spitzer Space Telescope, and then 10-meter class telescopes on the ground. The big thing that happens next that's really going to revolutionize this field in the immediate future is the James Webb Space Telescope. So this is a 6.5-meter infrared telescope. It's going to do spectroscopy from 0.6 to 28 microns, so it covers this huge range of all of these different molecular features that we think are going to be in these exoplanet atmospheres, and it's going to launch in the early 2020s, so it's currently slated for 2021. So what's this going to do for exoplanets? Well, I'm going to show you two different slides that show for kind of people with different scientific mindsets what you can do. So if you're really detail-oriented, if you want kind of the best data set that's really hard to understand and that you need to apply a complex model to understand, then hot Jupiters are your jam. So James Webb is going to get beautiful-looking spectra of hot Jupiters, both transmission spectra and emission spectra. This is showing an example for transmission of what we might expect for a clear or cloudy hot Jupiter. And it's going to be able to see all these molecular features and really understand the compositions of these planets in great detail. You'll also be able to see things like 3D effects. If the planets are non-uniform in their chemistry or clouds or temperature, we'll be able to measure that for hot Jupiters. So it's really going to be incredible, revolutionary. Then the second thing, if you're looking at all of these giant planet talks and you're like, no, I'm just here for terrestrial Earth-sized planets, James Webb is going to get towards being able to do that as well, sort of incredibly so. So this is an example of this for a special planetary system. This is for the Trappist One System, and this is special because it orbits one of the smallest stars that's even possible to exist and be a star. And so this turns out to help us a lot because the size of the planet relative to the size of that star is much larger. And so James Webb will allow us to detect the atmospheres of terrestrial planets around these very smallest stars if they exist. So really the science questions that we can ask for terrestrial planets with James Webb are things like, do terrestrial planets around the smallest stars have atmospheres or not? We don't know the answer to that question. There are lots of reasons to think that they might not retain their atmospheres. Okay. And in my last minute and 25 seconds, I want to talk a little bit about the more distant future and how what do we need to get to a place where we could detect something that's a true Earth analog, an Earth with, oceans and oxygen and nitrogen around a sun-like star. And for that, we need something more ambitious. And so what I'm going to highlight here is right now in astronomy, we're going through this Astro 2020 decadal survey, looking to the future to what we want to do in the 2030s. And so one of the proposed missions for that decadal survey is called HABEX. And so the idea here is that we're not going to be doing transiting planet science to see these Earths anymore. Instead, we're going to go to that imaging, to this really hard problem of blocking out the starlight. And instead of blocking it out with a coronagraph, we're actually going to build a whole star shade that's going to fly outside of our telescope to be able to block out the light. So this sounds like science fiction, but people are working on this in a very serious way. And so a mission like HABEX would be the first kind of mission that we think would actually be able to detect things like water, oxygen, and ozone in a true Earth analog. And the plot on the right is showing you what that might look like for a fairly dedicated amount of observing time of this type of planet, showing you where all of those molecular features would be. Okay, so I'm going to close there and say that we're now at a point where we are regularly detecting all kinds of different molecules, atoms, clouds in exoplanet atmospheres. I think there's a lot of places where we need expertise from the solar system that would allow us to better understand the complex physics and chemistry of these atmospheres. And I'm really looking forward to these future missions in the coming years and the coming decades that are going to allow us to detect atmospheres progressively more like our own Earth. So thank you very much, and I'll take any questions.
We have time for a question. If you have a question, please go to the microphone.
So I have a question. So geoscientists, we tend to think about volcanic gases, and is there any chance with these new atmospheric measurements to be able to tell if something is coming from a volcano?
Yeah, so you would need to be able to, you would need your volcano to be putting, especially if you're trying to measure it in transmission, you need your volcano to put the gas up into the stratosphere. So if it's doing that, which my understanding of volcanoes, which is very little, is that sometimes you have a large enough volcano that it goes up into the stratosphere. Then if you catch it at the right time, we think in the future you would be able to do that.
Great. Thank you. So we're now going to move to the next part of the session, which is going to be a panel discussion. So we're going to invite our speakers from the session to come up here, and our co-convener, Sabina Stanley, is going to moderate this session. There's going to be some questions that we're starting with, and then there'll also be time for questions from the audience.
Mix astronomers and...
All right, thank you very much. So we'll wait for everyone to quickly get settled in. And as mentioned, we are really hoping, my goal here is just to warm up the audience by asking a couple of questions, and the goal here is really that you're going to be asking the questions of our speakers here. So I guess we'll start. I'll ask a simple question to anyone on the panel who would like to answer, and ask that you limit this to a couple of sentences or so. But I want to know, and this is a dangerous question because it will force you to admit that you don't know everything, all right? So I want to know, what is the coolest thing you just learned in this session?
Yeah, I learned something really cool in this session. In recent talks, I've made predictions for what might be knowable in like the 2040s, and I have a wish list. And one of them is actually constraining the occurrence of plate tectonics in some way. And I learned a potential way that we could do that.
Anyone else want to chime in?
I guess on the same note, I found that incredibly exciting. Partially, in addition, because as we were just talking about, you might be able to detect volcanism in the future. Especially, when you have planets that are 2,000, in some cases, 2,500 Kelvin, you can actually really probe some of that very refractory material that those effects, that measuring those abundances and the predictions are that dramatic. I think that's really exciting in the future, and something I think even with Webb we may be able to observe.
Anyone else?
I'm more skeptical than I guess you guys are on that one. I was fascinated about the observations of the helium escape, and I had no idea that had happened this week. So thank you I have some reading to do.
Anyone else? Okay, so now I have another question. This one's going to be, I'm going to ask different flavors of it to different people on the panel. So I think I'll start with the more astro side of people and ask the astro people, what does the astronomical and the astrophysical community need from, say, the Earth or atmospheric or solar system community to understand exoplanets?
I really admired Carolyn's talk for putting forward individual measurements that we ask for. Like, broadly speaking, one of the reasons why I treasure planetary science so much and think that some of the most interesting results relevant to exoplanets have come out of planetary science is because it's possible to confirm in situ a lot of the measurements that we're forced to make remotely, and actually show us that these are valid ways of making measurements. I know that maybe that sounds skeptical, but I think it remains to be seen from testable predictions, whether these methods that we have for measuring remotely what's present in the atmospheres of extrasolar planets can be confirmed by using those exact methods on planets in the solar system. And I was most heartened by a study of Titan in transmission.
I guess just one follow-up thought on that. I think one thing that often gets underappreciated, I would say, by astronomers is how incredibly dependent a lot of what we do is on lab work that has been done by the planetary science and geoscience community. We are dependent on opacities, on reaction rates, on equations of state, on viscosities, almost, in some cases now, astronomers are trying to figure out how to do this themselves, but the vast majority of that is stuff that's come out of the planetary community. So in terms of things we would need, I guess just the one thing I would say is when designing those lab experiments, think big. Think, more parameter space you think is not at all physically possible might be possible.
Excellent. Carolyn, do you want to chime in?
Yeah, I'll echo the lab work, that having lab work, especially for some of the places where we have the biggest uncertainties that we don't think in some cases we'll ever be able to calculate from first principles. So one of the things I didn't talk about a lot, but is photochemistry and photochemical haze production is one of the things that's like super hard to do from kinetics models, but that people are starting to do now in the lab, much like they did for Titan for years. So I'd like to see more of those kinds of measurements using facilities that maybe already exist, but putting them under the conditions that we see in our planets.
Just to give you another concrete example from interiors, there's a problem that I think people have started to figure out in recent years is a lot of the exoplanets we're talking about, they're more massive than the Earth. And that means their interiors might be in different phases. So in my, Amy and Wendy would be much more of an expert, but in the Earth, at the core mantle boundary, you have this thin layer of, was predicted post-perovskite. A lot of the exoplanets we're talking about are 5, 6 Earth masses where the mantle will be completely dominated by post-perovskite. And my understanding, at least as of a couple of years ago, is we have no idea what the viscosity of that should be. That's incredibly important for some of the sort of predictions we want to make.
Indeed.
I'd also just, I want to commend Wendy in understanding each other's jargon. In particular, you brought up the water world issue, and I cannot tell you the sheer number of talks I've been to where someone is talking about a planet being 50% water, and then someone wants to ask them about whether it's habitable. So just understanding what paradigms each other is working in, what orders of magnitude, I think is really important.
So now let me turn that question around. So let me start with Amy, because it looked like you were about to say something. So Amy, can you tell us what the let's say the planetary atmospheric science community needs from the Astro community?
Sure. Time on your telescopes. Okay, I'm joking, but we do want that. But I think the other way around, it would be helpful for us to know what measurements would help exoplanets. And I don't mean just the remote ones, I mean the in situ ones. From our actual planetary missions, what would help exoplanets? So this could be the equivalent of a statement in your decadal or white papers to our decadal saying, hey, I really want to see this particular mission because it informs the exoplanets so much. I think there's a lot of complementarity. We tend to stovepipe a little too much. And so crossing those boundaries, I think, would help both communities. But from the planetary perspective, Europa is a water world, and I keep telling them no, Neptune is, right? So I think even within our own community, the jargon is a problem.
Okay. And last but not least, Wendy, what does the geoscience community need from the exoplanet Astro community?
I have kind of two separate requests. One of them is cultural and one of them scientific. The cultural one is that the geoscience community does not necessarily put all of their work on archive. And so read the AGU journals, where a lot of that, the material properties data are actually published. And there's discussion as to quality in terms of what makes a good measurement. So that's the cultural comment. In terms of the scientific one, when you find a planet where you can measure its mass and its radius, a spectral follow-up of its star, where you've quantified independently the abundances of the planet, the dominant elements in planets, magnesium, silicon, oxygen, and iron.
Okay, thank you. So I'm going to take a break from asking questions and ask if anyone in the audience has questions. And if you do, please go to the microphone. Yes.
So this came from a science fiction story I read some time ago when the objective was to see if planets were habitable. And the suggestion by the author was that you would never tell what the rotation of a planet was until you were very close to it, the tilt of the axis. Is that true?
It depends on what method and the planet itself. Jupiter's atmosphere, we can tell the rotation quite well because its magnetic field is tilted relative to the planet's rotation axis. So basically we get a beaming effect from the magnetic field. That does not work on Saturn. And actually, we just found from most of the Saturn session that the rotation rate we've been using for decades is probably wrong. And having Cassini there up close made a difference. So it depends on the planet, just to make this even more confounding.
And likewise, I would say that's also very much true of exoplanets as well. We have the only planets that we really have any rotation information thus far as the hot Jupiters. And actually, in general, these are probably planets that their interiors are probably not rotating. They're probably tidally locked because they're extremely close to their stars. But we do see the atmospheres have these incredibly strong winds that are rotating very rapidly. But yeah, interiors are hard.
I was a little upset by the fact that when we tried to infer Neptune's rotation period, we didn't get the rotation period. We got the speed of the cloud going around. So I think that's something that I think applies to some of the other observations that we've been doing in the field of exoplanets to try and measure rotation periods are going to have exactly the same problem because we have patchy clouds on them as well.
The one exciting bit, I would say, for future missions like HABEX and LUVOIR, if you can see planets where you can actually see surfaces and you can disentangle those surfaces from the clouds, from everything else, continents don't move on rapid timescales. So I think that could be very promising in the future.
Another question?
Yeah, this question was, I think, for Wendy, I think. So I like the idea of trying to learn something about the interiors, the actual solid interiors of exoplanets, which from the stellar composition, which I thought was basically going to be impossible. But when you were showing, unexpectedly low density planets and saying that was implying there was a water layer, can you actually tell if it's a water layer or if it's like a hydrogen, if it's like what Eric was talking about?
So we can distinguish low density from rock and iron, or from the assumption of the stellar abundance of rock to iron. We cannot, and in fact, the question that came before was there is also an additional ambiguity of, extreme amounts of oxidation, where you have a mantle that has maybe 5 times as much iron in it than the Earth does, would indicate that a planet actually contains more oxygen, which would lower its density as well. So no, we can't distinguish what the composition of that outer layer. I think the extreme oxidation is actually less likely. And that's where we would have these follow-ups with something like JWST to look at the atmospheres.
Okay, thank you.
If I could also just chime in one quick word there. I found that incredibly interesting. One system I would really love to see your analysis applied to in particular is the Trappist One System, since that is a system around, it's, for those who don't know, it's a very, very late M dwarf. It's barely a star, but it's also extremely X-ray active. And so it is a system where a hydrogen-dominant atmosphere would probably not be stable. So that might be a system where you could say they are definitely water worlds.
Yeah, it would be great to have the composition of the star.
I have a question that's maybe more of a general request of the planetary science community, or maybe a specific question for today, which is, what are the physical processes that do work across all planets in the solar system, at least to a factor of 2 level?
Gravity.
Because
Gravity.
they do exist. No, there must be more. You must have some insight into that. It's a serious question, because we don't care about all of the little details. We just want it to work to a factor of 2. And I believe that there are many more things than gravity that work better than a factor of 2 in the solar system across all the planets.
I think in atmospheres, fluid dynamics, the equations do not change whatsoever. The boundary conditions do. And that's been our biggest problem with getting GCMs to work across the solar system. The boundary conditions are quite different, whether you have a solid surface, whether you have layers, what the temperature profile is. So the physics part doesn't change, gravity doesn't change, but all the little details do, and it's the devil is in the details. You know, it's the butterfly effect. Every little tiny change anywhere on these planets affects everything, and that's kind of what we find in the solar system.
But to just push a little bit further, right? The band sizes of atmospheric cells, you can get that scaling across planets in the solar system, okay, right? All we need is okay.
You mean like overturning Hadley cell sort of thing?
Yeah, or like the width of the band compared to the size of the planet.
It's not uniform, and it depends a little bit on rotation, and it depends on
but
some
if you
other
know the
factors.
rotation
So that's why we see the banding on Jupiter, but it's not the same on Saturn. It's not the same on Uranus and Neptune. So there's no universal law to it. Every time we try to make universal laws, they don't work. We even look at energy cascade in atmosphere, similar to what gets done in astrophysics and, you know, Kolmogorov spectra. It doesn't work, you know, sometimes it does, sometimes it doesn't. It's very frustrating. It is those little details, unfortunately, that really do drive what we see.
I'd like to ask a question on behalf of, to use the phrase, a Joe Public. Thinking way ahead in the future, what would you need to directly image an exoplanet? You know, to get a picture that's suitable for putting on the cover of Time magazine. You know, like you know, an observatory that doesn't exist yet, or we'd have to build a probe and send it over there so we can get something that's half decent.
Yeah.
Well, we'll put our pale blue dot on the cover of Time magazine. To be frank, like that's what we're gonna get with a future telescope, is a pale blue dot, and it's gonna be beautiful.
Also,
Yeah.
can I put in a quick plug? If you're interested in that question, there's actually going to be a session Friday morning. I believe it's P51, specifically on the next generation future space telescopes, including Caroline mentioned HABEX. There's another concept that I'm involved with called LUVOIR, which are being studied by the decadal specifically to do that.
Oh, great, thank you.
And there will also be a poster session as well, so I'd be happy to talk some more. But I mean, we're not going to have resolved pictures, you know, with nice, beautiful continents on. But what we hopefully will have in my lifetime, hopefully our scientific lifetimes, are spectra and rotations, and you know, maybe we can learn about oceans and continents. But it is going to be an enormous effort.
There's one way that we could produce a map of sorts which is different from an image, which is from a phase curve. It's possible to do it if you have the relative brightness of the planet as a function of its phase, like as it's orbiting around the star. The reason that I thought of that was because such a measurement was done for the Earth from the Epoxy spacecraft, which was associated with the Deep Impact mission that crashed a probe into a comet. It turned and imaged the Earth, and then the person who led the study, Nick Cowan, who's a professor at McGill now, just took that integrated brightness, which is all you would ever get from a single pixel from an exoplanet, and he decomposed it. So he said, if you could only use 2 colors to reproduce the map of whatever this single pixel is, what would those 2 colors be? And he found that Earth was very well explained by blue and reddish brown. And he to speak coarsely for a planetary scientist, blue and reddish brown gets it about right. And that he reconstructed kind of an orange slice that you could recover continental features and so on. And that's another way that you could kind of, you could try.
Yeah, and
Well, that'd be
actually,
crazy too.
That technique was used for Pluto as well. The very early maps of Pluto were done in very similar ways, and when we got there, rough scale, they were right. So the method does work.
I should say that exact technique is something that these future telescopes are studying. There's a student, Jacob Jostig-Lager, that's going to be presenting later this week on the feasibility of doing that with things like LUVOIR and HABEX.
Well, that's all very exciting. Thank you.
Next question?
Yeah, I was actually worried he was going to take my question. I'm also not from the astrophysics community. I'm very naive on this, but exoplanets are cool, so I came to this session. Anyway, decades from now, again, if you have an opportunity to choose one instrument to place on a probe to send to an exoplanetary system, knowing the bandwidth limitations and all of that and how long it's going to take you to get the data, what would that one instrument you want on that probe to be?
I am loving these questions.
Oh, well, I can pass on a piece of advice that I got from one of my planetary science colleagues, which is always put a magnetometer on your instruments. And, I mean, in all seriousness, hopefully we can build a large enough telescope that we can probably get good spectra. But what you can't do is do close flybys. So things like Juno, if you just had a radio transmission back that's precise enough, you can measure gravitational moments, and you have a magnetometer, I think that you would learn an immense wealth of information you couldn't get any other way.
Can we stick the camera from my iPhone on too, just so we can get a nice picture?
Yes. Also, always have a camera.
I would also like to point out that I did not force Eric to say magnetometer when he did that. Any other answers to that? Sorry, anyone else want to? No? Okay, then we'll move on.
So say there was a planetary science community that was about to go through a process of prioritizing missions for a space agency for, say, a period of time like 10 years or so. And among the types of things that I would imagine people in the planetary science community would want to do would be exploring Venus and exploring ice giants. And I'd be curious if one of those or the other would be of more value to improving our understanding of exoplanets. I'm hearing Venus being whispered at me, but I want 10 missions to every body in the solar system. So,
I mean, I think you learn very different things. I would love to, as someone who studies atmospheric escape, I would love to know a lot about Venus's atmosphere. As somebody who's interested in interiors, I would really like to know what on earth is going on in Uranus's interior. I think it's. I think that's a question above my pay grade, but I think they are. All of these missions have strong implications for the exoplanet community.
I guess I am thinking about known exoplanet systems. So if I wanted to have an understanding of the Trappist system, for example, which has around this really small star that got mentioned a handful of times, it has a number of planets. I forget how many reside in the nominal habitable zone of the star, and they're all 4, greater than or equal to 4, I think. And they're all like approximately the size of Earth. I'm very curious then, that's a system that could potentially be a Rosetta Stone for us. What is it about one planet that it's of a particular size and receives a particular amount of insolation that makes it habitable and its twin is not? And that's a question I think could be answered with a mission to Venus. It's what came to my mind first.
Any other answers from the panel?
Then I'm going to hog the microphone for one more second with Cayman's permission. And I'd like to, in the interest of advancing this kind of interdisciplinary discussion in this field, I'd like to invite everyone to consider attending the Gordon Research Conference on Origins of Solar Systems, which is going to be held in Mount Holyoke, Massachusetts next summer, next June. It brings together cosmochemists and astronomers and modelers to discuss all these issues of how solar systems form. There's a very strong exoplanet presence this coming year. So Google it, you'll find it, and please come.
Thank you. Next question.
Hello, thank you for a series of great talks. So as we kind of move forward in the field of exoplanet science, I feel like we're venturing more deeper into the realm of science fiction. So my simple question is, to that end, what are your thoughts on the goals of SETI, and does it fit into, could it have a place in the scientific field? Thank you.
Yeah, I think that, look, I mean, a lot of what we're focusing on as people think about HabEx and LUVOIR, these future mission concepts, is thinking about astrobiology and being able to detect biosignatures on these kinds of planets. But of course, technosignatures would in many ways be more interesting, right, to see signals of, well, equally interesting, I guess, to see signals of intelligent life. So I am personally pro studies of these technosignatures. I'd like to see more of that, figuring out what the best way is in a modern society, right, kind of with more imagination than just using radio telescopes. I think there could be lots of other ways of looking for intelligent civilizations.
Another interesting aspect of this is, much like we've seen in any of these systems, whatever we find always kind of turns over our knowledge entirely. If we got a signal, SETI found something, it's almost certainly going to be from a system we didn't expect. And that's going to be the part that throws all of our paradigms to the wind. And so I think that's going to be the most interesting thing that'll come from something like that. So, I see no harm in searching. We need to know eventually what else is out there.
I was going to say, I think there's another really important piece to things like SETI or the piloted spaceflight program, which even though I might not pick them first, like if I had a limited amount of money and I only got to pick one mission, I don't know that I would allocate money to SETI over and above other things, but it doesn't mean that there's not this like multi-axial space of how scientific missions function as a product of the cultures that they're drawn from. So I feel like SETI serves this function, which is also to inspire the imaginations of people in the same way that the piloted spaceflight program does, even though, relatively speaking, it's much more expensive and dangerous than sending a probe or something like that. But in a time when cultural literacy of science is sort of like perilously in danger, I feel like having things like SETI, which space is one of the like very few, what's it called when all parties like, when both parties in a system like agree on something? It's like a what's it? Bipartisan. It's one of the like few bipartisan things that remains is like support for space. And for that reason, I actually would be in favor of it too, over and above the scientific impact.
I think, yeah, it's very much, it's a both and, it's not an either or. I think if you really want to answer the question robustly of let's find out how common is life in some form, or if it's not common, let's get a definitive upper limit on that, then you do need this multi-decade, very careful, very expensive approach to try and directly image planets to look for biomarkers. But on the other hand, if, for a tiny amount of money, if you get that techno-signature, the efficiency of it, it's high risk, but it would completely revolutionize the entirety of humanity. So I think it's worth that, what essentially is pocket change compared to the total amount we're investing in science.
Just like pointing out, the SETI is almost entirely privately funded at the moment, not publicly funded.
Yeah.
Okay, let's move on to the next question.
So first of all, I want to say I appreciate this session. I'm actually really interested in seeing in the future more collaboration between the geology, planetary science, and the astronomy community. And so going off from that, how are we going to move forward, and how are you going to be able to facilitate discussions like this in the future, especially not only for current scientists and professors, but also for rising scientists, postdocs, graduate students, and undergraduate students?
One thing that I was going to say that I feel like is a very useful avenue to pursue with respect to our communities coming together is actually co-advising students. It's something that I've thought about in the past being something where if communities are sort of equally invested in the career outcome of a young person, that's such a universal feeling, even where jargon might fail and a number of other things. And I also feel like that kind of co-investing in an individual is also co-investing in a field where individuals will be fluent in the understanding of exoplanets and in planetary science. Not unlike you, Janelli, doing research in both like geophysically relevant things and exoplanets, sort of the student of the future.
I think another thing we need to do is to avoid the arrogance of our fields where we know the answer and nobody else does. And a couple of years ago, we had an AGU Chapman conference actually to try to cross those boundaries between Earth science and planetary and exo, because the Earth scientists have vastly different data sets than we do. Their stuff doesn't necessarily apply all the time to ours for various reasons. Yet you'll hear planetary science say, "We're doing this so we understand the Earth," and the Earth scientists do not like that for obvious reasons, because it's an arrogance, and I think we have to get away from that. We have to understand there's things we don't know. And having these cross-disciplinary discussions, whether it's a workshop, it's a panel, I think they're really, really important so that we can understand each other's science and then work together.
Also, I would say, just as a quick comment for those of you who are on admissions committees, I think it's one flaw, I would say, of a lot of astronomy departments, which is where I came from, is they traditionally prioritize people from physics backgrounds. Many departments require the physics GRE, and it's often having a good understanding of quantum physics is often prioritized over people from more geoscience backgrounds. And I think for departments that are invested in exoplanets, think seriously about those and try and take people from other backgrounds if it might fit with the research that you're interested in.
I was also going to pan the physics GRE, but also, in addition to the co-advising approach, invite people to your seminar series that come from other disciplines and spend some time talking to them. Run something like, there's this concept that we think we're viewing with blinders. Help us out. And I've seen a lot where people, it's like, I've seen a lot of earth science or earth scientists work on some of these fields where they're like, oh, there's a knob I can turn, and they turn the knob, and they don't understand that next level of the astronomy. And so, some of the results are interesting.
Okay, we have time for one more quick question.
Okay, well, she stole most of my questions, so good job. But I wanted to come back and touch on Wendy's culture point from earlier in the panel. And especially with publishing, I think there's a real problem with publishing for the exoplanet community in that there is not a good home where both astronomers and planetary scientists can publish and get people to read the same set of articles and so come to a similar sort of understanding of the issues that we're dealing with. In particular, when sort of geoscience articles get submitted to, say, astronomy journals where there's only one reviewer, and maybe that's not the right reviewer for that paper. And so I feel like it's sort of mixed the literature up a little bit, and so we have some results that might not be as rigorous as they would be if they had gone to a different journal.
Yeah, just as though there's a donut hole in the graduate education, there's the donut hole in the publishing.
Correct.
Steve,
yes.
you have
At this point, I'm required by law to encourage all of you to submit your exoplanet papers to
Right.
JGR Planets. We very much welcome exoplanet papers.
Yes, so I just wanted to get the thoughts from the panel on where do you see as the best place for publishing in order to get everybody to read your articles. And yes, editors
I've
in the room
not succeeded.
are welcome to
not
in.
succeeded in that area. It is
Yeah.
a real problem.
Well, I think wherever whatever journal it goes into, it has to go in the archive because that's like literally the only thing we read.
And yet the
But
archive,
like Science and Nature let you. How can you have journals that don't let you?
and yet I feel like the archive has shown recently with their unilateral banning of research notes that they're not that egalitarian. So maybe they're not the best place. So maybe we can start the discussion on coming up with a better place to submit
The
those
planetary
journals.
journal Icarus for a while was pushing really hard to get exoplanets, but nobody outside of planetary reads Icarus. The astronomical, the AAS journals were pushing really hard to get planetary for a while, and now they have a new policy. If you submit, say, an AppJ letter, it goes to astronomical journal. So now they're pigeonholing all the planetary back into one journal. So I don't know what you do, but...
At this point, I'm required by law to let you know that AGU has a new open, an archive-like place where you can deposit all of your papers. It's called SOR. And there are there's Earth Archive, which is a non-AGU place as well, which is intended to try and fill this role that Archive has for a long time in other fields. Unfortunately, we are out of time. I would like to thank our panelists once again and remind you that this is the beginning of a new effort. So come to AAS and you'll hear more about exoplanets.